Today we'll be looking at enthalpy and calorimetry. Alright, we are going to be doing a little something different today, and here's what we got. Ooh, here we go. You're excited to see it? New ink color. Nice. Alright, so enthalpy. This should be following right along in the outline we're doing. Whoa, enthalpy, not enthalpy. Alright, so enthalpy is the heat of a system, and its symbol is H. It's usually measured in joules or kilojoules, but really the heat of a system. This is something that was covered in general chemistry, and we're just going to go through it kind of really quickly here. Number one, H or Q. Enthalpy is essentially the same thing as heat if the pressure is constant. Okay, and in just about every sense, pretty much even in AP chemistry, certainly in everything we did in general chemistry, and really in AP chemistry, for all intents and purposes, heat is enthalpy. All right, but it's really only enthalpy if pressure is constant. And we're going to say that Q equals E plus P delta V. If you look at your notes from just the other day, 8.1, this is just a rearrangement of that last equation I showed you. I think that there was the example 6.1 in your textbook that I had you look at. And since PV, or P delta V, is small, we can say H approximately equals E. Or it's close enough. Okay. Number two, delta H. Let's see. Delta H is the heat either gained or lost by the system. Heat gained . And I think that is all I want to say about that. We'll kind of keep on going. How is delta H calculated? It is always H final minus H initial. Really, this is kind of just a side note. This is important and it applies to a question on your test. Delta H, or we've already looked at delta E, these things are known as state functions. In state functions, just the dead giveaway that something is a state function. State functions have a delta as part of their equation. In state functions, really the idea is it doesn't matter how you get from point A to point B. All that matters is what is the difference between point A and point B. So kind of real quickly, we have a mountain, and we've got another mountain. They look like triangles, that's fine. But you have a hiker, and this hiker kind of meanders from the base of the mountain, kind of does this thing up to the top, and he ends at the top, he or she. This other hiker just goes, I don't have time to do this. I'm going to go from the bottom, and I'm going to go right to the top. So which of these hikers hiked a longer distance? And we would say hiker L, the east or the west hiker, hiked a longer distance. The east hiker or the hiker on the right hiked a shorter distance. But who climbed a larger altitude? And the altitude is going to be the same. So the change in altitude, although this doesn't really work that well, altitude is identical for both hikers, equals the same. Okay, they both started at the base of the mountain, they both ended at the peak of the mountain. Who cares that hiker A, or the west hiker, went longer? What matters is the change. Okay, so state functions are anything that has a delta in front of it. and just as long as you have that. So we'll go back to our lavender. Alright, so delta H equals H final minus H initial. And if our delta H equals a positive value, we would say heat is gained, and this is endothermic. Alright, kind of just like our notes from the other day. If delta H is negative, heat is lost. Heat is gained. That's excellent English. That's alright. Heat is lost, and that would be an exothermic reaction. So again, heat is gained by the system, or heat is lost by the system. So system is always what we're concerned about as far as heat is either being gained or lost. And I guess real quick, how do these typically feel to us? Endothermic reactions generally feel cool to the touch, and exothermic reactions generally feel warm or hot. Alright? So our hand would be the surroundings. So if we put our hand up to something that is giving off heat, that energy is being absorbed by our hand because it's being lost by the system and it feels cold to us. If heat is being gained by the system, our hand is the surroundings, we grab that, it is leaving our hand going into the system, so we are losing heat from our hand, therefore it feels cool to us. Alright? Next thing, heats of reaction. Heats of reaction. These are delta H of reaction equals delta H of products minus delta H of reactants. Okay? Which is still the whole final minus initial idea. What do we finally end with in a chemical reaction? Products. What do we begin with? Reactants. So that is still final minus initial. If we have this equation, methane as a gas plus oxygen as a gas yields carbon dioxide as a gas and water as a gas. If we balance this, 2 C's, we need 2 waters and 2 oxygens. I think we're good. So 1, 2, 1, 2. But if that is balanced, typically an equation like this will have, you'll have the equation, and then generally off to the right, I didn't leave enough room over there, it's going to have delta H of reaction is negative 802 kilojoules. Okay, so this reaction is negative 802 kilojoules. It's negative, okay, so heat is being lost. This is exothermic, which makes sense. We are combusting methane. Same thing we do with a Bunsen burner. If we put our hand up close to a Bunsen burner, it feels hot. Alright, so a couple things with this reaction. The first thing is delta H of reaction is an extensive property. Which means it depends on how much we have. Okay? It also means that it depends on stoichiometry. Depends on stoichiometry. Therefore, 1 mole of CH4. I forgot to put mole there. So 1 mole of CH4. If we reacted 1 mole, we might do a little kind of conversion like this, where if we look at our balanced equation, 1 mole of CH4 is equivalent to negative 802 kilojoules. Okay, so this value in energy is related stoichiometrically to 1 mole of methane, 2 moles of oxygen, 1 mole of carbon dioxide, 2 moles of water. And this is true, we get negative 802 kilojoules. However, if we had 2.5 moles of methane, so if we reacted more methane, we would release more energy, because a mole of methane always releases negative 802 kilojoules. So in this case, we would release negative 2005 kilojoules of energy. Okay? So just know it's an extensive property. It depends on how much we react. And not only does it depend on how much we react, but it does depend and relate in a stoichiometric relationship. The other thing we can kind of look at with this equation is delta H of reaction. Delta H of reaction for reverse reaction. So if our products were to become our reactants, and our reactants were to become our products, delta H reaction for reverse has same magnitude but opposite sign. So if we were to rewrite this equation just the opposite way, so we're going to react carbon dioxide with 2 moles of water, and they react to form methane plus 2 moles of oxygen. Our delta H of reaction for this reaction is going to be positive 802 kilojoules. Okay? If we reverse the reaction, instead of giving off 802 kilojoules, it's going to require 802 kilojoules. The other thing, and this is, we have not worried too much about this yet, but state symbols do matter. So our last little bit on this, delta H of reaction depends on states. Depends on states. So if we were to change this, or if I were to give you this second equation, 2 moles of water as a gas, or really, doesn't matter that it's 2, just water as a gas, if we condense it into liquid water, alright, that gives off 88 kilojoules of energy. Okay, that process, going from a gas to a liquid, it gives off energy. It's an exothermic process. So if we were to have this equation kind of again, methane plus 2 moles of oxygen, this is methane gas, this is oxygen gas, yields, and what was it? Carbon dioxide gas, and now 2 moles of water as a vapor or liquid. If we look at our first one, which was negative 802 kilojoules, right, and this reaction is negative 88 kilojoules, what happens is basically this gas, which is on our reactant side, cancels with this gas on our product side, and then this liquid becomes our new water on our product side. So essentially we add these 2 kilojoules and find that our delta H for this last reaction is simply delta H, it's negative 890 kilojoules. Alright? The last thing we need to do is calorimetry. Alright, so we kind of looked at how equations worked, but then determining delta H. Determining delta H. And we determine delta H by a couple different ways. The first way is that we can measure it directly. And in order to do that, we use a process called calorimetry. And everybody in general chemistry should have had some sort of calorimetry experiments. You should have had one in college as well. But really, a couple words, just definitions you need to be aware of. Heat capacity. And heat capacity is the amount of energy needed to raise temp of object 1 degree Celsius. Alright? And then we also have the molar heat capacity, which is going to be the same thing, except it's going to specify a specific amount of the substance. So this is just the amount of energy needed to raise the temperature of an object 1 degree. Molar heat capacity is ditto amount of energy needed to raise the temperature of an object 1 degree if we have a mole of the object. So you might say amount of energy needed to raise 1 mole of an object 1 degree Celsius. And then the last thing is specific heat capacity. And this is more or less what we talked about in general chemistry, probably your college chemistry. And it is the same thing. So ditto, except it is the amount of energy needed to raise a gram of a substance 1 degree Celsius. Amount of energy needed to raise 1 gram as opposed to 1 mole. 1 gram, 1 degree Celsius. And a couple ones that you need to be familiar with for water. It is given the unit C, or the equation C. And usually it's C lowercase p, and this is just, again, say constant pressure. We can measure energies if our pressure is constant. So the Cp for water is 1 calorie per gram degree Celsius. Or, because our relation between calories and joules is 1 calorie equals 4.184 joules, it's also 4.184 joules per gram degree Celsius. And then we have this nifty equation, which is Q equals mc delta T, which again is just a way of us to measure directly H. Because again, I mentioned that Q is H at constant pressure, where m is the mass of our object, C is the specific heat, which you'd have to get from some sort of table, and then change in temperature, which is always T final minus T initial. And that is what we covered in your ChemQuest that we did in class today. So this last equation should be very familiar to you. Alright, so the main thing is, I think number 3 might be new stuff, how we can manipulate the delta H equations. If we reverse them, we reverse the sign. We're going to be adding them, so we're going to see that state symbols are really important, and I think that is it.